so it's not recording. Okay, so on this quiz, we have this compound over here, and we need to figure out what it looks like in pH 7. First thing you got to remember is what does the protonated form and what's unprotonated form look like. Whenever you have a nitrogen, right, you can have it look like this. What's the other form of a nitrogen? It can have three bonds in one lone pair. I can draw it this way if you like. Or it can have 4 bonds. And what does it need if it has 4 bonds? A positive charge. Okay, out of these two, which one has the additional proton?
The bottom one.
Bottom one, there's an extra H. Remember, H is our proton.
Right.
So this is the protonated. This is unprotonated. You don't need to write any of this down.
Wait,
I'm just going over this to show you what the protonated and the unprotonated form is. Whenever you have a carboxylic acid, you can have 2 forms, the protonated form and the unprotonated form. It can look like this, or it can look like
A whole bunch of them.
this,
What if you didn't draw your dot?
right?
What if? Never mind. I drew my dot.
No, you're supposed to draw the lone pairs.
I won't take off if you didn't draw the lone pairs. Oh, that's fine, that's good, that's good. So, which one of these is the protonated guy? The one on the top or the bottom?
Top.
Because it's got more protons and this one doesn't, right? So this is the protonated,
Right.
this is the unprotonated. Okay, that's just background, right? Now we got to figure out the answer to this thing. We want to know this at pH 7.
Right.
Okay, what's the Henderson-Hasselbach equation?
pH equals pKa
pH equals pKa plus log.
parentheses A minus over HA.
Very good. How many people put that on their paper? Good. Okay. Now the big question is how to use this sucker to give you an answer. So, we want to work on the left side first or the right side first?
Left.
Okay, we'll work on the left side first. pKa is 9. We know we want to look at this at pH 7, right?
Yeah.
So pH equals 7. The pKa equals 9. So 7 equals 9 plus x. What does x have to equal?
-3. 2, I mean.
-2. So if this thing equals -2, if the log of some number equals -2, what's the number? What's this?
10 to the -2.
10 to the -2, right? Log of 10 to the -2 is -2. It's just the exponent.
Right.
When you're trying to figure out what's in here, you're just going backwards. You're just taking 10 and putting whatever number is here as its exponent, right? So whatever number you get here, you just put 10 to that number. And that's what's inside the parentheses. So 10 to the -2, another way to write that is 1 over 10 to the 2, right? So which would you have more of? The A minus or the HA?
HA.
HA. So you'd have, that's the protonated or unprotonated form?
Protonated.
Protonated. We said the protonated form looks like this.
Right.
So that would mean on this side, it looks like that. So what about the other side? Okay. Now
Well,
the
no, you gotta
pH.
solve it first. So then you put 3.5.
So pH is 7. I told you the pKa of this thing is 3.5.
And 3.5.
3.5 plus x equals 7. What's x?
3.5.
Okay, so that means I'm talking about 10 to the 3.5, right? So another way to write that, since it's a positive up here, is just 10 to the 3.5 over 1, right? So when you're looking at this ratio, which do you have more of, the number at the top or the number on the bottom? Number on the top is bigger than the number on the bottom, so you have more of this. Which form is this?
Unprotonated.
Unprotonated. We said this was the unprotonated form. So over here,
Erase that H.
we have to erase that H. And that's what this sucker looks like at pH 7.
Oh, so we got 100? Great.
Okay?
And I wrote all that.
Huh.
And I did all that.
It's one compound.
I still got it right.
It may have a bunch of different pKa's, but you look at each individual
I know.
functional group and just figure out what's that functional group at the pH that they've told you. It's going to be the same pH, because you can't put it in a solution that's got different pHs, right? It's just got, it's a solution, so it has whatever pH it has. Pull out a sheet of paper. Pull out another sheet of paper.
Oh, I'm gonna feel this one.
Would you like another bite at the apple?
No, 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 no,
No,
no,
no,
no.
no, I got 100. I don't take them all.
No, I wrote all of that on the paper.
Anybody here want another bite at the apple?
They can get that.
Okay.
Wait, what if you ain't circled? Because I ain't circled.
Yeah, it doesn't matter whether you circle it or not. Okay.
Take off points and you didn't right now.
That's what I'm saying. That's why I have to Because I think it's 60 points that I have. I didn't
What I'm trying to do, my biggest concern is that you guys learn this. Okay? How many of you think that you can do this now? Raise your hand. Who's still lost? Okay, what are you lost at?
Honestly, the whole thing, I wasn't here last class, so I didn't understand, like.
Okay. Rather than the whole thing, so somebody else who doesn't understand something, what is?
That, structure part you're talking about. Like, I get the math part, but when you add to do the structure.
Okay, so you have to remember that whenever you have a carboxylic acid, there are two possible forms you have. Which form you have is determined by the pH of the solution. Because the pH, remember what pH stands for is the negative log of H plus concentration. These are just free protons. And so the lower the pH, the more free protons you have. Okay? And so if your pH is really low, you're going to have tons of free protons running around. If you have this, you'll probably stick a proton on it and get that, depending if you have enough. If you have this form, if you got enough protons around, you'll stick one on there and it'll look like that. Okay? And so the first thing to know, if you're completely new to this, is it's only these two functional groups you got to worry about. Okay? Carboxylic acid has these two forms, and amine has these two forms, right? We call this form of it the carboxylate, the one that's missing the hydrogen, the unprotonated form, okay? So, whenever you're looking at, however I've drawn this, I'm assuming a certain pH. When I tell you the pKa and the pH, you can figure out, all you're trying to figure out is whether it's an O negative or an OH. That's all you're trying to figure out on this one. On this side, you're trying to figure out if there are 3 hydrogens or 2. That's all you're trying to figure out. And so the math just tells you, if you have the A minus one, that's the one without the proton, which would mean if this was A minus, then this would just look like that. If you have more of this one, if this is the bigger number, then that's the protonated form. It means you have it like that. So all you're trying to do with all that business is try and figure out whether or not you got a proton there or not. Whether or not you have a proton here or not. Whether or not it's protonated. That's what this HA stands for. This means protonated, because that H, remember H's are protons. A hydrogen atom is a proton and an electron, right? And so an H is just a proton. H pluses are just protons. They're missing the electron, so it's just a proton. Okay? And so all you're trying to do on this is figure out which side is protonated, whether it's protonated or not. I always give you the pKa, and I'll tell you what the pH is. Okay? Now, there's also a shortcut. So, I'll give you the reasoning behind the shortcut. If we have a low pH, a really low pH, what is that saying about the proton concentration? If you got a low pH, what does that say about the protons? You got a lot of free protons in solution. That's what an acidic solution is. There's tons of little protons around. Okay? That's why acids tend to degrade substances. When you pour an acid on it, it starts to decompose and shrivel up. It's because all those free protons are attacking the bonds, and you're making bonds with the protons, and it's breaking the bonds in the compound, and that's why the compound decomposes. Okay? So if you got a low pH, lots of protons around. Again, I'm giving you the rationale behind the shortcut. I haven't told you the shortcut yet. One other good thing to know about this is, what is the definition of the pKa? Okay, and this is going to be a question I'll ask. What's the definition of pKa? That's going to be on your problem set. Okay? The definition of pKa, if you don't know it, write it down. It's the what? It's the pH at which?
Half the species are protonated, half the species are unprotonated.
Very good. Half the species are protonated and half aren't. How do we know that? Because if half of them are protonated and half of them are not, what is this ratio? If these two numbers are equal, what is this ratio equal to? 1, right? If you have the log of 1, what's that equal to? What's the log of 1?
0.
What number do you raise 10 to get to number 1? 0, right? So that means when these two are equal, this turns into 0, and the pH equals the pKa. Therefore, the definition of pKa is it's the pH when this thing goes to 0. Okay, which is when these are half and half. So the pKa is the halfway point. Okay? Different compounds, based on their electronegativity, are going to have different halfway points. Okay? So this guy, the halfway point is 3.5. This guy, the halfway point is 9. Well, what did we say is true if your pH is lower? You got more protons, right? So if your pH is under the pKa, you're below the halfway point, you have more protons, so you must be in the protonated form. So your shortcut is, if the pH is below the pKa, it's, what is it? Protonated or unprotonated? If the pH is below the pKa, it's protonated. Period. This is always true. This is always true. And the way you can see that is, it doesn't matter what numbers we use here. If the pKa is higher than the pH, if the pH is lower than the pKa, that means we have to add x has to be a negative number, right? If x is a negative number, then it's going to be 1 over 10 to whatever the x is, right? So that means this number is going to be bigger. This is the protonated form. So whenever the pH is smaller than this number, this thing has to give you a negative, which means you have more of this. So whenever the pH is below the pKa, it's protonated. So I could have just come here and said, well, at pH 7, the pKa of this is 9. Well, at pH 7, I'm below the pKa. It's got to be protonated, so I'm in this form. What do you think is true if the pH is above the pKa? There's fewer protons around the higher your pH is, right? And so on the top side, if you're on the other side of the halfway point, because we know the halfway point, you're half protonated, half unprotonated. So you're going to go, if you start out protonated and you're at low pH, you go past the halfway point, you're now going to be unprotonated, right? So look at this side here. We had the pH was 7, the pKa was 3. So the pH is above the pKa. We determined this guy to be protonated. So I could have just said, oh, well, the pH is above the pKa, it's got a proton on it. Simple as that. I mean, you can go through all of Henderson Hasselbach if you can't remember which way the rule goes. Because this is the way, it's easy to to misremember it and say, well, if the pH is below the pKa, is it protonated or unprotonated? It's always protonated in this case. Okay, so you could remember this rule, but if you can't remember that rule, the Henderson-Hasselbach equation always gets you there. Okay? The way I remember it is, this is an amino acid, by the way. Amino acids look like this at pH 7. That's what amino acids look like at pH 7. Carboxylic acid at pH 7 is always negatively charged, and the amine group is always positively charged at pH 7. Amine groups, their pKa is always going to be above 7 because they're bases. And carboxylic acids, any acid, its pKa is going to be below 7 because it's an acid. And so the way I remember it is I just always remember, well, amino acids are zwitterions. They got a positive and negative charge. And so this, if we're talking to pH 7, I know amines have a pKa above 7. So the pH is below 7. It's protonated. Okay, I got it. I always remember that carboxylic acids look this way at pH 7. So you can do it any one of the three ways. Just decide what works for you. So now we get to the more challenging part. This is what we did last time. So now we're going to go to a titration. So we can learn a lot from a titration. You're probably all wondering, why in the world do I care about this? I'm never going to need to know any of this. How many of you feel that way already? Remember, I'm teaching you everything you need to know to understand the other stuff. So this is all part of a bigger picture. Remember, the most powerful of the non-covalent forces are ones that deal with charges, right? Your ion pairs. Those are going to be what helps determine the structure of a lot of things. Important parts of the structure and how they behave. So you need to know whether something's going to be protonated or unprotonated. So we're going to do a titration curve. Matter of fact, we can use that same amino acid. Anybody know the name of this amino acid? This is alanine. You're going to have to memorize all 20 of them. They're 3-letter code and they're 1-letter code and be able to draw their structure. That's alanine. Okay. It's got 2 ionizable groups. So what happens if you're going to titrate this? And do you know, what does it mean to titrate? It means you slowly add base or you slowly add acid and you watch how and you're trying to pull off a proton. Like when you titrate an acid, you're trying to neutralize it with base, right? You're pulling off the proton. Don't worry, you don't need to know that.
Oh, we're going back to that graph.
So this, along here, when you do a titration curve, this is pH. Label this axis pH. Do from 1 to 12, 1 to 14, whatever you like, whatever you need. Okay? And then this is called equivalence of OH minus. So hydroxide ions. Okay? So we're going to start from a really low pH, which means it's really acidic, and we're slowly going to add base. Okay? If it's really acidic, if we're down here at pH 1, what does this guy look like at pH 1? Right, you're going to be protonated, right? Because we know the pKa of this is going to be above 7. I think before I said it was 9. And we know that this one's below 7, but I think I said it was about 3.5. But we're at 1. And if your pH is below the pKa, you're protonated. So this guy would be protonated. That's what he looks like. Is this the protonated form of this side? No. No, we need H3+, right? Yeah. That's the protonated form. So down here, that's where we're starting from. If we're at pH 1, this is what it looks like. Now we start adding base, okay? And these OH minuses, what are they going to want to do? If you've got an OH like this, what do you think this thing is going to want to do? It's going to want to, what does it want? What kind of atom does it want? Another proton, another hydrogen, because we all know this one, right? That's a really stable molecule. This is kind of high energy. This is lower in energy. Okay? So it would spontaneously like to pick up that proton. So it's going to go around and try and pick protons up from the easiest place that it can. Okay? Whoever's willing to give it the protons the easiest. It can either get the protons from the solution. In a pH 1, there's a lot of protons in solution, right? Because that's the definition of low pH. Lots of free protons. Or it can pull the proton off of here. Okay? To pull all the protons off of here, you'd need an equal number of OH molecules to pull off this one, and another equal amount to pull off this one. Right? So if you had a mole of this, say you only had this. If you wanted to pull off all these protons, you'd need a mole of OHs just to pull off all of those protons. Okay? But this guy has 2. So you need a mole of OH take off these protons and a mole of OH take off those protons. There's 2 ionizable groups in this one. So that means in terms of equivalence of OH, it's going to take 2 whole equivalents. An equivalent is an equal amount. So for every one of these, you're going to need 2 OHs to pull off both protons. So on this axis, you'll look to see how many ionizable groups you have, and that's the end of your axis. So we have 2 ionizable groups. So here's 2, here's 1. Okay? And so now we start pulling off. We add hydroxide to the water base. It starts grabbing protons. The easiest protons to grab are going to be the ones from the water, because there's just a bunch of free protons around, at least right now. And so this thing starts to scavenge protons, and since you're pulling protons out of the water, the pH has changed, right? Because pH is the concentration of free protons. So your pH starts to change as you add OH. That makes sense. Yeah, but as you get within 1 pH unit of the pKa, you now start pulling them off of this guy. Okay? Now, 3.5, which guy is going to lose his proton first? The carboxylic acid or the amine?
Carboxylic acid.
Yeah, it's the halfway point for this is 3.5, right? So what I like to do when I do these graphs, I say, okay, my first pKa is 3.5, and I just draw a dotted line across at the first pKa, and then I look at the second pKa at 9, and I draw my dotted line across. And I know that the definition of pKa is the pH at which half of them are protonated and half are not, right? Well, so that means at pH 3.5, half of these are going to be protonated, half of them are not going to be protonated. Well, how many OHs or how many hydroxide groups did it take to do that? Well, if it's going to take a whole equivalent to pull off all of them, then it only takes a half an equivalent to pull off half of them. So I go over here and find where my 0.5 is. And so right here, I know that's a point that I know about on my graph. Is at half of an equivalent, I'm going to have taken off half the protons of here. It'll be at its halfway point, half protonated, half not. So that means that the pH is now equal to that pKa. And so when I go to draw my graph, I know that as I get close within 1 pH unit of my pKa, this thing starts to balance out. Now, as I get close to 1, remember it was going to take me 1 whole equivalent to pull off all these protons. Okay? As I get to 1, it's still, I'm pulling off the protons off of here, so my pH of solution isn't changing. That's why I'm adding equivalents of OH, but my pH isn't changing because I'm pulling the protons off of here instead. But once I get to 1, I've pulled off all the protons from here. And so as soon as I start adding more OH, where am I going to get the protons from? The solution. And so the pH is going to change again because now the free protons in solution are being eaten up. And so now my pH will change very rapidly as I add my OH. Okay? Well, let's look at this group. The pKa for this guy is 9. Okay? So I know at pH 9, that's the halfway point. Half of them are going to be protonated, half are not. Well, I know it's going to take, after I'm done with this guy, I knew it would take a whole equivalent, an equal number of these to remove all of them. So half that number would get me halfway. So what's halfway between 1 and 2? 1.5. So I know that right here is my next inflection point. I know when I use another half of an equivalent, I'll take half the protons off here. And so I'll have half and half. That's the pKa, that's the pH. And so I look on here, I remember that it's within 1 pH unit that I start to flatten out. And then once I get to 2 whole equivalents, I'll have pulled off all those protons over there. And if I keep adding OH, my pH is going to change rapidly because I'm just pulling them out of solution. And so this is what the titration curve looks like for this compound.
So I have a question.
Uh-huh.
Because I know in the previous graph you said, when we was at the pKa, it was at the half point, like,
Mm-hmm.
it was like kind of like a straight kind of, so like, is it like when you have 2 areas?
So you'll see these flat areas, we can call them whatever we want, we can call them flat areas for right now. You'll have one flat area for every one that you have a pKa for. For every ionizable group, we'll give you one flat area. Your inflection point will always be at that pKa at either a half of an equivalent, 1.5 if you had 3 ionizable groups, it'd be a 2.5. The straight lines come either at 0 or increments of 1. Because once you've pulled off all the protons off of this guy, now you're pulling protons off of solution, so the pH changes rapidly.
Okay.
But when you get close to this guy's pKa, now you're getting close to the point where this guy is weak. Okay? Now his proton is dangling now. At lower pH, it was on there real strong, but now you're getting close to its pKa, so it's getting point to the part where it gets loose, and now your base is pulling the stuff off of there, and so the pH doesn't change. Even though you're adding lots of OH, the pH isn't changing all that much, because you're pulling it off of that guy, and then it goes back up. Okay? This is exactly, and the reason why we have you do these graphs is this explains exactly what a buffer is. This shows you what a buffer is. Because remember, a buffer, when you have a buffer in solution, it's supposed to maintain the pH. Right? And so you can add a little bit of acid or a little bit of base and the pH doesn't change much. Well, look at this. If you've got this compound in solution and you're around pH 3.5, you could add a little bit of OH, but the pH doesn't change that much. You could add a little bit of acid and the pH wouldn't change at all. Because you're just pulling the protons on and off of the compound, not out of the solution. And the pH is determined by the free protons in the solution. Yeah?
So at that, are these inflection points?
Yeah, we can call these an inflection point. In math,
So
that's
like
what they'd be
you're
called.
halfway there, then you lose the first solution. Halfway there, you lose the second solution, you get a straight base?
Mm-hmm.
Okay.
You got it. And so this compound, say you wanted to have a buffer, say you had a protein that worked at pH 3.5. This would be a great buffer to use because if you had a lot of this around and you got your protein in solution, if you added acid, the pH really isn't going to change that much. I mean, you could add enough acid that eventually you get down here. You'd have to add a whole equivalent. So if you're at 1 molar of this as your buffer, you need a mole of acid to get to the point where you're out here, and your pH starts to change again. That's why the buffer concentrations are so high relative to whatever other stuff you're working with. So this compound actually could buffer at this pH or at this pH. So here's another thing to write down in your notes. This will be on the MCATs. A compound is a good buffer within 1 pH unit of its, what am I going to say? Of its pKa, right? Because that's where the flat area, right in the middle of that flat area is that pKa, of its pKa. That's why, like if I go down to 2.5, it still hasn't, that's why I start making this over here start to flatten out at around 2.5, because that's within 1 pH unit of 3.5. And then once I get to about 4.5, that's when you'll be way over here. Okay, so we're going to do this again with a different compound, so because I'm sure some of you are barely hanging on by a thread. So we're going to do this for
Oh, I'm ready to go. You want your stuff?
we're going to do it for this compound.
Where I do the titration curve?
Yeah.
You want hers? She want yours, Chan.
Oh, I didn't need to make this.
You do that? Oh.
I know. I was moving too fast. I was at
Okay. So we're going to do the titration curve for this compound. First off, how many ionizable groups does this have? There's a carboxylic acid up here, and there's a carboxylic acid out over here. Okay? So that means I need to have given you 2 pKa. Right? So we're going to say the pKa for this guy, we're going to say was 4. And we're going to say the pKa for this
I'll
guy
ask him, but I'm pretty sure
was
we don't have
equal
to
to
worry about it.
6.
What about the F since it is electronegative?
It is that's actually what's making this pKa lower, but there's no proton to play with. You can't protonate a fluorine. It can only make 1 bond.
Yeah.
So it will have an effect on this by lowering you don't have to worry about why it lowers the pKa. It's just more electron withdrawal. Stabilizes that thing. But don't worry about that.
So, like you said, for the most part, we just have to worry about oxygen and nitrogen when it comes
Yep.
to this
And
class.
for this stuff, amines and carboxylic acids. Okay? And so when I go to do this, the first thing I do, I see I got 2 pKa's. I draw a dotted line. My first pKa, 4. My next pKa is 6. I draw another dotted line. Since I have 2 ionizable groups, my equivalence of OH goes up to 2. I know at half an equivalent, I'll put a little dot at the first pKa, and at 1.5 equivalents, I'll put a dot at the next pKa, and then I'll just draw my little line. Flat. Remember, it goes up at about 1, goes like this, and then go up at about 2. That's my titration curve for that compound.
Oh, okay.
Wait, you just did it so fast.
What now?
You just did it so fast. Can you go over?
Sure. Sure, let me start over. When I first start drawing this thing, I can draw this, but I don't know how many equivalents of OH I'm going to go to. I have to know the number of ionizable groups. Say I had this guy over here. Now I have 3 ionizable groups, right? So that means I need to have given you 3 pKa's, right? pKa 4, pKa 6, we'll say pKa equals 10. Okay? So since I have 3 ionizable groups, how many equivalents of OH is going to take? No, 3. 3 equivalents.
That's it.
Uh-huh.
That was an H before, right?
Yeah.
I was drawing it. Sorry.
Okay. So I need to go up to 3 in this case. Because there's 3 ionizable groups. I need to have 0.5, 1, 1.5, 2, 2.5, 3. So now I find what my pKa's are, and I draw my dotted line. First pKa is 4. Second pKa is 6. I'll draw another dotted line. And third pKa is what? 10. So I'm going to draw a dotted line up here. Okay? So now I remember that the pKa is the halfway point, and the halfway point is going to come when I add a half an equivalent. So first one down here. Now the next halfway point is going to come at 1.5 because it took one whole equivalent to get rid of all of these protons. And then it's going to take another whole equivalent to get rid of all those. A half of an equivalent would get rid of half of them. So there's my halfway point at 1.5. Where's that halfway point going to go for equivalents? 2.5, right? They're always at the 2.5s.
Gotcha.
It's always at the half mark, basically.
Yeah. Your inflection point is at the, because it takes half an equivalent to pull off half the protons. A whole equivalent pulls off whole proton.
So why wouldn't you start at 1 for
Well-
a whole equivalent?
Well,
Oh, it starts there at that one.
yeah.
Okay, gotcha.
Okay. So then I just draw my lines. Remember, they go up at 1 and 2. And that's my titration curve for something that has 3 species with those 3 pKa's. Okay. So, and what's wild about this is you can take a compound and you can put it at pH 1 and say you put a mole of compound in there, or 2 moles, whatever number of moles you put in, you can precisely measure as you add OH, it will follow, the pH will follow this exact amount. If you put in 1 mole of that compound, then when you put in a half a mole of OH, you'll get to this pH. You'll add a little bit more, the pH won't change, and then all of a sudden when you've added a whole mole of this, now the pH starts changing a lot, but then it'll slow down again. It's 6. And you'll be adding OH and OH and OH until you get to 2 moles. pH doesn't change at all. Until you get to 2 moles, then all of a sudden the pH starts to change a lot as you add a little bit of OH. And then all of a sudden it'll start to slow down again as you get close to 10. And the experiment will match this exactly. And that's kind of neat. It's matched what you predicted mathematically. Who knew you could predict equations or predict experiments using math? That you could do it, because you can't. Okay, so now, this is the complicated part. Okay, this is the part that always freaks people out on tests, is whenever they give you this kind of question, they'll give you the compound, they'll give you the pKa's, they'll tell you to draw the graph, and then they'll want to know what the compounds look like in the different ranges. Oh gosh, right. Oh gosh. So, when is the compound going to change? The halfway points are these inflection points, right? So, The first region is between here and here. Yeah, you're not saved by the bell yet. I got 2 minutes. Okay? The first, we already know this though. This isn't that tough. What does the compound look like at pH 1? All the things are protonated, right? Because if the pH is below the pKa, all of them are protonated. So this is an OH, this is an OH, and this is an NH3+, right? Okay, so in this region, until you get to this first halfway point, all the compounds up as you're adding OH, all of them here are going to look like this, right? Yeah, the structure is going to look like this. So this structure that I've drawn right here, with this guy protonated, with all three protonated, is in this range here, right?
Okay.
Now, what's the next range? In between here and here, what does it look like? Well, when we cross this bridge, when we go through the halfway point, who's changed on here? Which one is changed? The top, the bottom, or the middle?
The bottom.
The bottom one, he changed. What happened to it? It's no longer protonated, right?
Yes, unprotonated.
Because now your pH for this guy is above the pKa. Here
Yeah.
he's still below.
Yeah.
Here he's still below.
Right.
So now
He's above
the
it.
guy for this region is going to look like,
It's a whole nother structure.
yeah, it's a whole other structure. That guy's
It's gonna be
protonated.
the same.
This
It's
guy
gonna be the
is
same.
the same, only now this guy down here is different. He is now unprotonated with the negative charge. Okay? Because
Yes,
you're going
he's
to lose
unprotonated.
this
He's
protein.
unprotonated. You're right.
Yeah.
You're right. He's unprotonated.
Okay. The next region comes after between these two halfway points.
So now the top will about to change.
You're going to change this guy, right? He's going to lose the proton. Another structure. So in that range,
It's gonna be
it's going to look like the
electric.
guy without this.
Right. And then that one too. It's gonna be
And then once you get past this, then your pH is going to be above all three pKa's, which means they're all going to be unprotonated. And so it'll look like
So
that.
you don't have to worry about the problem. I mean the equation for this.
No, the equation in that reasoning gets you to the same point. You could do the equation every time, or you could just remember that when your pH is below the pKa, you're protonated.
It's protonated.
And if your pH is above the pKa, it's unprotonated. And so what I'm going to ask you is to draw the structure for each region. Remember, the regions change when you get to the inflection points.
Right.
You start out with everything protonated because you're below all the pKa's.
Here you go.
And then slowly, one by one, you pull off a proton from the lowest pKa guy to the next highest.
Can we just not have
Yeah, somewhere in there.
I got it.
Okay.
Y'all should
I should have, okay, I'm going to try and have the problem set.